Okay, so it's 1 o'clock. I assume some more people will join, but maybe not. Who knows? You do have the option of attending asynchronously, so not a big deal. Um, any questions before we get started? Okay, so we're gonna continue on with Module 5, and today we're gonna talk about space, the final frontier. Of course, I had to make that joke. So um, we're gonna talk about extraterrestrial stratigraphy, which hopefully you'll notice bears a lot of similarities to terrestrial stratigraphy. But before we do that, some announcements. So any questions on any of that? Okie dokie, let us get right into it. So we're talking about extraterrestrial stratigraphy today, but let's just kind of talk about terrestrial stratigraphy real quick. So when we talk about stratigraphy, especially when we talked about it in historical geology, the first thing that we said were like, the first thing we established were these like stratigraphic principles, these like super basic, almost like common sense stratigraphic principles. At the time, though, they were pretty revolutionary. It was the first time that people really looked systematically, or at least the first recorded time that people looked at it systematically. So the first one here is the law of superposition. The younger layers of rock sit on top of the older layers of rock. So like the laundry basket example, you start with an empty laundry basket after you've done your laundry and you folded it and you put it away nicely. Yeah, right. You get home from school on Monday, throw your clothes into the laundry basket. The stuff on Monday is on the bottom of the basket. Get home from Tuesday, get home Wednesday, Thursday, Friday. The clothes pile up in an order. And if somebody wanted to be a creeper, they could come in and look at your laundry basket and they could tell what order you wore your clothes in based on the superposition, the stacking, the ordering. That would be very weird though. Don't do that. The next thing is the law of original horizontality that says that layers of sedimentary rock are originally deposited flat. So original horizontality, rocks are originally horizontal. Anywhere where gravity exists and sediments are being deposited either in some sort of fluid, whether that be wind, whether that be water, whether that be liquid methane, whether that be any kind of fluid, fluids are restricted, they're kind of self-leveling, and if gravity exists, the deposits are going to be level and flat, roughly. We talked about some dipping strata that can be like crossbeds, things like that, but they're relatively close to flat. They're not dipping at 80 degrees. The next one, that's relatively straightforward, law of cross-cutting relationships. So here you see C, this intrusion here is cutting across B and A. So you know that A is younger than B because of superposition. And you know that C is younger than both because it cuts across them. You can use faults. You can use even like with footprints, you can tell like footprints in the snow. You can tell order of footprints by which is cross-cutting what. Just kind of a common sense thing. You can't cut across something that's not there yet. If there's a fracture cutting across a rock, the rock had to be there before the fracture. If there's a vein cutting across another vein, that older vein had to be there first. And then the last one is law of lateral continuity. Rock bodies, sediment bodies don't just abruptly stop. They're laterally continuous until they kind of pinch out or something else removes them or they hit some kind of barrier. So those are the stratigraphic principles that Steno established on Earth way back in 1669 with De Solido, essentially of solids. And we use these for stratigraphy on Earth, and we also use them for stratigraphy in space. So let's talk about some space stratigraphy. So let's go to the moon. So basically everything beyond just looking through a telescope started with the moon. So we didn't really have any way of doing stratigraphy just by looking through telescopes. You could roughly kind of potentially date some things, but really it began when we landed on the moon, or at least flew by the moon very closely. So the Soviet Luna probes were actually the first to photograph the far side of the moon, sometimes called the dark side of the moon, That's kind of an Earth bias thing. It looks dark to us, but when you're on the other side, it's not. Sometimes that's the light side of the moon when we're in a new moon phase. But anyway, the Soviet Luna probes photographed the far side of the moon, and the Luna 2 probe actually impacted the surface. So that was kind of our first ever interaction with a celestial body. We crashed a probe into it. The Soviets at this point were pretty far ahead of us in the space race. They had the first object in space, Sputnik. They had the first dog in space. The dog didn't make it. They had the first human in space, Yuri Gagarin. And we were kind of far behind. But America, we eventually came through. The Apollo missions were the first to actually land on the moon. And 6 of the Apollo missions actually successfully landed. It kind of got so commonplace that the American public kind of got bored with it. Like, I can't really fathom the idea that landing on the moon is so common that we wouldn't even really care anymore, but it kind of got to that point. And that's one of the reasons why Apollo started to kind of fade. People stopped paying attention. But throughout the course of those missions, not only did we get invaluable looks at the surface and looking at the geology, but we also brought back about 842 pounds of moon rocks. So these missions actually brought back rocks. These are the only rocks that we have from outside of Earth that are not asteroids. So the moon, not only do we have pictures of the moon, we have really good detailed maps of the lunar surface. We also have actual hard rock data. And we've actually had a geologist on the moon. So Harrison Schmitt, one of the Apollo 17 astronauts, he was one of the last people to walk on the moon. I think he was second last to walk on the moon. He was a geologist. He wasn't an astronaut. He's one of the few, I think maybe the only person that was just a scientist. He was trained as a scientist to walk on the moon. And here he is doing some pretty routine field work. So he's actually doing geology on the moon. And here you see kind of that kind of bland, dusty regolith lunar surface, but there's also some big chunky rocks here. And obviously this is the first picture here with you see the rover and the actual landing craft there. So pretty cool. We have actually conducted field geology on the moon with an actual real trained geologist. So let's talk about how the moon formed first, and then we'll talk about stratigraphy. So the moon and the Earth have been kind of paired together since relatively early in our history. So after the Earth formed about 4.6-ish billion years ago, allegedly, the leading hypothesis is that there was a massive collision with another body, kind of about the size of Mars almost. So a massive body impacted Earth, just a massive collision, blew out this disk of debris, and that disk eventually coalesced into the moon. You see kind of an artist's rendition here. Obviously, we didn't have any pictures back then. Looks like this hellish landscape. Again, this is the Hadean period of Earth's history, when the Earth's surface is basically all molten rock. The atmosphere is toxic to us. It looks nothing like modern Earth. It looks like Hades. It looks like hell. And Theia collided with that. And one of the pieces of evidence of this is that stable isotope ratios, basically the chemistry of Earth and the moon, are pretty near identical, which suggests they formed from the same body, probably through this collision. One thing that's a little bit different is that the moon has a lower density. It has a very small iron core. This is probably due to fractionation after these things impacted. So Theia hit the outside of the Earth. The Earth had already density stratified, so the denser stuff was in the core. The less dense stuff was in the outside. When that smashed in, it kind of blasted out more of the lighter material, and that became the moon, and a lot of the heavier stuff was kind of left behind, which is why Earth, maybe one reason why Earth is the densest of the rocky planets, because a lot of that light material was blasted out to form the Earth. So what does the lunar surface look like? So the lunar surface has a lot of these kind of bright, rough, rugged area, the highlands, and it also has some of these darker, smoother areas called the Maria, which is Latin for sea. So if you look at the highlands, and we can, because we've actually been there, and we've brought back rocks. This is a lunar rock sample. The highlands are primarily made out of anorthosite. If that sounds familiar to you, it should, because if you go to the high peaks, the highlands of the Adirondack Mountains, Mount Marcy, for example, is a big anorthosite intrusion. A lot of the high peaks are anorthosites. There's some other scattered anorthosite bodies around the Adirondacks, like Snowy Mountain is an anorthosite dome. There's a couple other very smaller ones, but the high peaks area is a massive amount of this anorthosite. It says here andesite. Anorthosite's just a different flavor of andesite. So I don't want to get into igneous petrology, and I couldn't even if I wanted to. But anorthosite is a very felsic rock, that light, less dense material that was probably at the crust of Earth during the Hadean that got blasted off into space. Later on, with probably, you notice how a lot of the Maria are roughly circular in shape. These are mostly flood basalts that occupy what's probably very large impact craters that formed relatively early in the history. You'll notice they're much less impacted than the highlands are. They've sort of been resurfaced over time with these lava flows. So let's look at lunar geology. So we have photographed the entire lunar surface. We've driven rovers around the entire lunar surface. We have walked on, not a large portion of the surface, but we have walked on the surface. So we've actually mapped the lunar surface with a combination of actual legitimate field work, remote sensing, and then also using relative dating concepts. Again, those Steno's principles of stratigraphy, superposition, cross-cutting, yada, yada, yada. So we have actually, this is a geologic map of the moon. This is the near side, the side that faces towards us. So remember, the moon is tidally locked. The same surface is always facing us. And then this is the far side of the moon, which we didn't know what it looked like at all until those Soviet probes. We could never see it. It was always pointed away from us. This is the quote-unquote dark side of the moon. What you'll notice is that there's a big discrepancy in how cratered it is. So the far side is heavily cratered. The near side is not. There's a lot more of these large maria on the near side. And you can also see that just like an Earth geologic map, there are geologic units. So let's look at how we define those geologic units. So if we look at lunar stratigraphy, there's actually a lunar timescale. So just like there's an Earth geologic timescale, Cambrian, Ordovician, Silurian, Devonian, blah, 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 blah. There are lunar periods as well. So there's the Nectarian, Imbrian, Eratosthenean, and Copernican. And these are all defined based on changes in impact craters and also volcanic activity. So if we look here, we've got like a pre 3.87 billion year volcanism event. And you'll notice it says Apollo 14 on here. This is defined from samples that were collected by Apollo 14. Here's some rock samples collected by Apollo 11 in a different part. Apollo 17, Apollo 15, Apollo 12. Some Russian Luna probes establishing mineral content and things like that. But these breakpoints here are defined by major events. So like the Nectarian is defined by basin and crater materials, some of the larger basins, and then very specific craters like the Krieger crater or the Lambert crater, or especially the Eratosthenes crater, define the Eratosthenean period. And then we get into the Copernican system, which is defined by the start of the impact of the Copernican crater. So this stratigraphic framework is mostly based on relative timing. So we can look at craters and we can say like, okay, well, this crater cross-cuts that crater. This crater is younger. We can use these relative dating, or this ray from this crater overlies this crater, and we can say that that one's younger. But what's unique about the moon well, not unique because we do it on Earth all the time, is that we have the relative timing, but we also have absolute timing. So we're able to constrain the relative time framework, and we can actually put some dates on it. So we have some time constraint for these relative ages. So overall, the stratigraphy is defined by relative big events, but we do have some absolute radiometric dates to do that. So it actually allows us to kind of calibrate our relative dating techniques. We can use techniques to try to date these events that do not rely on age dates, and we can then test them using the age dates that we do have. That's something that we don't have the luxury of doing on, say, Mars. On Mars, we have to rely entirely on relative dating. And so the fact that we can kind of test these ideas on the moon is great. So one of the things that we can do is, again, superposition. So relative dating is really simple when things are stacked up. When things are stacked up, the oldest stuff's on the bottom, the youngest stuff's on top, or again, cross-cutting. So like in the example of craters, this is a very old crater. You can kind of barely make out the circular pattern of that crater because it's been heavily modified by younger craters. Here's a slightly younger crater that hit in there. Here's a slightly younger one as well. What you'll notice is that there's two smaller, even younger craters that hit that one. And so you can date these impact events by seeing how they interact with each other. Another thing that you can use for dating is when an object impacts the surface, it blasts out debris, ejecta, from the pit. And so what we see here is there's a lava flow, a dark basaltic lava flow that flowed into perhaps an older crater, an older, much larger crater. Here's a crater impact. We could date with just the crater impact, but what you see is that the debris fell on top of that lava flow. For the debris to fall on top of that lava flow has to already be there. That means that the lava flow is older than that impact event. And another thing is that these flood basalts, the mare, they tend to fill craters, they tend to fill depressions that are older than the flows themselves. And then younger craters tend to pit the surface of these smoother flows. And so we can use all these different relative dating techniques to try to constrain the timings of these events, the relative timings, older or younger. And in relatively limited cases, we can say like, okay, this is younger, but it also has this particular date, because we do have some absolute ages. Another technique that we can use is crater density. So the density of impact craters can be used as like a relative like proxy for geologic age. So the longer a surface is exposed, the older a surface is, the more time it has for stuff to impact it. And so like a very old lava flow should be impacted by way more craters than a relatively young lava flow. And so we come up with this curve here of crater density on the moon, because not only do we have the crater density, we have some age dates. So these little crosshair things here are age dates from all the Apollo missions and also from the Luna missions. What we see is that there's a clustering of a lot of really dense cratering here. Then the crater density kind of tails off, and then it really drops off. So using the moon and using the crater density that we observe on the moon, you basically take a square area and you just count how many craters are in there. And then for the moon, we actually have samples that say like this area that has this given crater density is this age. And so we're able to construct this curve. And what we see is there's a lot of cratering early on in the moon's history, early on in the age of the solar system. Over time, as the Earth is revolving around the sun, and as the moon is revolving around the Earth, they're sort of clearing their paths of all this debris. Early on in the solar system, there's lots of stuff floating around. There's lots of stuff colliding. In some cases, really massive stuff like Theia. Over time, that stuff all became assimilated and aggregated into the Earth. We basically swept it all up. Our orbit is much clearer now than it was back in the day because our gravity either chucked that stuff out into space or pulled it in and it crashed into us and became part of the Earth, like the dinosaur killing impact or the Theia impact. And we see that decrease over time. We've cleared the orbits, and then a relatively constant for a while, and then it really kind of drops off recently. And so the fact that we can use the moon to kind of calibrate this curve, it really establishes a benchmark of how much stuff is floating around in the solar system at a given time. And we've kind of made the leap that the stuff that's floating around in the solar system around Earth and the moon is comparable to the amount of stuff that's floating around in the solar system next to Mars, next to Venus, next to Mercury, next to all the other planets. And so we can kind of use this impact curve to establish relative time frameworks on other planets that we don't have any hard data for. Another thing that we can use is relative erosion data. So on Earth, we think about erosion, we think of weathering, we think of breaking down solid rock into soil, into sediment particles that get smaller and smaller over time, and the chemistry composition changes over time as well. We talked about that earlier on in the course. You don't really have those processes per se on the lunar surface because there's no free water. There's really no wind to speak of. But there is a lot of cosmic impact. And so one process that you're breaking solid lunar rock down into smaller lunar quote-unquote soil or regolith is you smash rocks into it. You're mechanically breaking up that sediment from impacts. Another thing that can happen is agglutination, where you're actually fusing things together from impacts. And then something that's slightly less important is that there is a small amount of cosmic bombardment. So the moon does not have an atmosphere. There's nothing to protect the moon's surface from being bombarded by cosmic energy, the solar winds. Our atmosphere blocks a lot of that stuff out, not 100%. There's actually a dating technique on Earth, a relative dating technique that's used a lot in glaciology called cosmogenic dating. Over time, when rocks are exposed on Earth to cosmic rays, they change over time at a relatively known rate. And so you can actually date when rocks are exposed by glacial weathering by seeing how much of this alteration has happened. This also happens on the moon, this alteration, and these little tiny micro impacts build up over time. And so what happens is that right after an impact, the crater is very steep. It has this raised rim. It might even have like this little raised center peak. The ejecta, the rays that come off away from it, are very bright, very luminous. And then over time, the rim gradually decays. The rays from the impact ejecta gradually decrease in brightness. You might have some floods into the crater, but basically over time, the crater becomes less and less recognizable. You'll notice that it also over time accumulates smaller craters within it. Again, the longer that surface is around, the more time it has for stuff to smash into it, the more likely that it has a record of other impacts. And so this is another relative dating technique that we have. And if we look at kind of a theoretical cross-section of the lunar surface, we have intact lunar crust here, fractured crust that's not really moved any significant portion, but it's fractured from all these big impacts. Then we have structurally disturbed crust. You see the scales here. This is like 10 kilometers, 2 kilometers. These are like big blocks that might have been moved around by impacts. Here's large scale ejecta, and then the really fine grained dust that we think about with the boot print down into the dust. That's like the upper 10-ish meters or so. And in some areas where the craters are deeper, they get through the regolith and they're exposed in the craters themselves. In some cases, you can see stuff that almost looks like layering in the craters from these superposed layers. Okay, so why are we talking about this? This is SedStrat class. We're supposed to be talking about stratigraphy. We're focused on Earth mostly until this point. Why do we even care? Well, basically, if we look at Earth's surface, if we look at the geology of Earth, if we look at the distribution of rocks on Earth, as you know, the geologic quote-unquote record is actually a lot more gap than it is record. The geologic record is highly flawed. There's tremendous amounts of time missing in these major unconformities, and even these little tiny paraconformities, disconformities, these times of non-deposition. There's a lot more time when nothing is being deposited, when we don't get any glimpse at the story, than there is when we are seeing strata deposited. So one of the only ways that we can look back into the Archean, the very earliest portions of Earth's history, if we want to do that in field geology on Earth, there's very few places that we can go. The old core cratons of the continents is the only place that we can go. As you see, these are few and far between, and they're also incredibly highly deformed. These things have been smashing into each other for 4 billion years. They're being buckled, folded, buried, metamorphosed, squished and squeezed and strained, and over time you lose the ability to kind of work out the story. It just gets too complex. The farther back in time you go, the more orogenic events there are, the harder it is to tease out. The Adirondack geology is very difficult to work out because it's so complicated. So many different orogenies warping those rocks in so many different ways over so long a time period. So if we want to look at what's going on in the Archean, rocks that were floating out in space that very closely resemble the early history of a planet, those are like little time capsules, little windows into the history of the Earth. If we're able to directly observe a rocky planet in the earliest stages of its development, that would be super informative to how the Earth formed. We haven't really gotten to that point yet, but we probably will very shortly. Another thing that it kind of teaches us is that it shows us really the limits of uniformitarianism. So James Hutton, this idea of deep time, this idea that the processes that we see today are the processes that were at work yesterday, and geology happens very slowly over very long periods of time. That's mostly true, but there was always this debate between uniformitarianism on one hand and catastrophism on the other hand. It turns out that both are at play. So like most of geologic history is slow, steady processes of seas go in, seas go out, erosion, deposition, erosion, deposition. But occasionally we have these massive events, like Chicxulub is a very good example. That's a relatively unprecedented event on Earth's history, as far as we know, and it radically altered the biosphere, at least, of Earth. It ended the age of reptiles and ushered in the age of mammals. Without that Chicxulub impact, we probably wouldn't be here. We probably wouldn't be contemplating our existence because mammals would never have really been a thing and they never would have evolved into where we are now. So we have to keep in mind that sometimes catastrophism is a thing. Sometimes radical, quick geologic events alter the course of the planet. It also lets us kind of look at the controls and the impact of various tectonic processes. Earth hasn't always had tectonics, but the rock record that we have that's relatively consistent and relatively quote-unquote good, that was deposited in the era where we had like modern plate tectonics. If you go back into like the Archean and the Proterozoic, that's not necessarily true. But for the Phanerozoic, where the vast majority of our rock record is, it's basically modern plate tectonics. if we want to look at what a planet looks like that doesn't have plate tectonics, or is in the last stages of plate tectonics, or is in the first initial stages of plate tectonics, Earth is a very bad laboratory for that, but other planets might be amazing for that. We'd be able to look directly at what's happening, or maybe in some cases not happening. And it also gives us an appreciation for things that can happen from outside of the Earth. We usually talk about, at least in stratigraphy, we talk about allocyclic processes and autocyclic processes inside the basin and outside of the basin. We don't really think about things that happen outside of the planet. And again, Chicxulub radically altered the course of Earth history. That's something that was outside of the planet. Or you can argue that the Deccan Traps was maybe more significant, but regardless, the meteor impact was a huge event. So if we put that all together, we can start kind of working out a relative history of the solar system. Earth is not very good at that because Earth is constantly being resurfaced. We're constantly adding new rocks. We're constantly removing old rocks. But the other rocky bodies are a little bit more likely to show us hints of the very earliest history of our solar system. If you look at this graph here, it's percentage of the surface. So this is 100%, 0%, and this is age in billions of years. The Earth is 4.6 billion-ish years old, but the oldest rocks on Earth are really about 4 billion years old. We don't have that history preserved in the earliest portions. Now there are some minerals that are from like early in that history, so like zircons are really hard to kill. We have a lot of zircons that are older than that, but they're minerals that have been sort of eroded out from whatever rock they were part of. They show us that Earth was solid by that point, but they don't tell us much else. Asteroids are the only record that survives from this period of time. The Moon and Mars show us what was happening on the solar system at this time. Earth doesn't. Earth's really good at showing us what's happened recently, but it's really bad at showing us what's happened long ago. The other planets are sort of the opposite. Venus is sort of an outlier here because Venus was basically completely catastrophically resurfaced somewhere between 500 and 700 million years ago, and basically all that old information was lost. But this is why we're doing this. This is why we want to look at extraterrestrial stratigraphy, because it can help with terrestrial stratigraphy. It provides some insights into our planet, in addition to helping to understand other planets and also beyond our solar system. All right, so let's take a look at Mercury. So my very educated mother just made 9 pizzas, something like that. Is that how it goes? Mercury is the first one. So Mercury is the first rock from the sun. Its surface roughly resembles the moon. So this is a shot of Mercury's surface. It doesn't have the really high color contrast of the highlands and Maria of the moon, but if I just showed you this picture, you might say, okay, well, that's the moon. It looks very similar. One of the most prominent features on Mercury is the Caloris impact basin, which is 800 miles wide. This is an impact crater on the planet's surface that's 800 miles wide. That's enormous. This was a huge impact, so huge that it sent shockwaves all the way through the planet, and it actually disrupted the surface on the direct other side of the planet called the antipode. So there's pode where it actually hits, and antipode directly on the opposite side. In the past, some people had proposed that the Chicxulub impact at the Yucatan Peninsula that ended the dinosaurs is what triggered the Deccan Traps eruptions in India, because it's roughly antipodal. If you do the reconstructions, it's not really. There's a pretty wide margin. It's almost the whole width of the Indian Ocean. But the Deccan Trap eruptions, which are massive, are roughly on the other side of the globe from where the Chicxulub crater impacted. So, you know, it's probably just coincidental, but at least there's a minor coincidence there. Another problem with that theory is that the Deccan Traps were probably already erupting when Chicxulub happened. And so that again complicates this story of what actually killed off the dinosaurs. Was it the impact, or was it this massive flood basalt eruption in India? The answer is probably that it was a little bit of both. Certainly neither one helped. But this might be a good analog to that, although the Chicxulub impact probably wasn't large enough to actually do this. Another thing that we see that's kind of weird with Mercury is that Mercury is missing a lot of mantle material. If you look at Mercury in cross-section, there is a lot of the higher density core material, and then there's a relatively thin mantle compared to Earth. This is probably a result of a massive impact that basically stripped away all the mantle material and kind of left the higher density core stuff behind. One thing that we also see on Mercury's surface is that the impact craters are shallower, and the ejecta fields are much smaller than on the moon because Mercury is bigger than the moon. Mercury has a higher gravitational field, and so the stuff just doesn't fly as far. So Mercury's exploration history, it's the least explored of the inner planets, so we know the least about Mercury. We really haven't made it a priority. And the reason for this, or at least one of the reasons for this, is that the surface of Mercury, now remember Mercury is the first planet closest to the sun, it has ridiculously large temperature range. The side facing the sun is 400 something degrees C, and the side facing away from the sun is negative 280 degrees C. Think about trying to build a rover that would, or a probe that could withstand those temperatures. The other thing is that just like a figure skater, when they're trying to do twirls, if they want to go faster, they bring their arms in, and if they want to go slower, they put their arms out. The closer you are into the sun, the faster that revolution speed is. Mercury's the closest to the sun, it revolves the fastest. And so if you're trying to send a probe or a spaceship to intersect it, it's very difficult because it's moving really fast. To get to Mercury, you have to actually use a gravitational kind of slingshot to accelerate the probe to intersect its target, and it's very difficult. So there's really only been 2 probes that have really made it to Mercury and gave us any kind of real data. This is an image from Mariner 10 in 1973, and this is more modern from 2008 Messenger, which mapped the entire surface. Eventually it even crash landed onto the surface, so we got some more information with that. But we don't know a whole lot about Mercury, but that doesn't mean we don't know anything about Mercury, because again, we have this relative impact curve that we sort of established from the moon, and we calibrated with the moon, and we make the assumption that the same conditions were true of Mercury. And so even though we have a complete absence of actual samples, we have literally no rocks from Mercury, we have literally no absolute age dates. All we have is relative dates, but we do have this curve that we've calibrated from the moon. And so kind of just like the moon, these major stratigraphic intervals are defined by major events, major impact events, major volcanic events. And so it's broken up into the Tolstoyan, the Kaiorian, the Mansurian, and the Kuiperian, based on trend curves, changes in trend on this impact curve. And so we're actually able to kind of roughly date the geology and sort of start to establish a relative dating framework based on this data. You'll notice that it's a lot less detailed than the map of the moon. We just know a lot less, but we do know something, and it's sort of useful. So my very, Venus is the next one. Venus is often called Earth's twin because they're roughly the same size, which means that they're also roughly the same density, which means they have roughly the same gravity. Venus is very, very similar to Earth. You see here they are to scale. Mercury is quite a bit smaller. Venus is almost exactly the same size. Mars is a little bit smaller. So Mercury is the closest to the sun, and we talked about those incredibly hellish temperatures, that really wide temperature variation. Venus is a little farther away from the sun, so you would think that, okay, well, that's fine. We're a little farther away from the sun, it's going to be a little cooler. That's what should happen. So Venus's surface temperature should be 232 C, or sorry, negative 41 C. It should be really cold, but it's not. The surface temperature is actually 462 C. It's much hotter than it should be based on its distance from the sun. So why is that? Well, it has a very thick atmosphere of carbon dioxide, and so it's basically this runaway greenhouse effect. Energy comes in and the infrared can't get out. It's trapped by these massive thick blankets of carbon dioxide. We are starting to make our own little thick blankets of carbon dioxide on Earth. It's not possible to really get to this point, but we don't want to even start heading that way. Another thing, it has clouds of sulfuric acid. So this is a very, very hostile environment. Because the atmosphere is so thick and it's made out of really heavy elements, the pressure on the surface of Venus is the equivalent to being about 3,000 feet below water. So if you ever swam down to the bottom of a swimming pool, like say 10 feet deep, your ears might pop and you might feel a little bit of pressure and maybe even pain on your ears. Now think about diving to 3,000 feet. You can't do it. It's not possible. You would be crushed. That's massive amounts of pressure. So Venus's surface is very highly inhospitable to humans. That's one reason why we generally talk more about Mars than we do as Venus. There's also the atmosphere is also rotating very quickly, and the upper parts of the atmosphere reach extremely quick, very fast wind speeds, basically sustained hurricane force winds, above hurricane force winds really, in the upper parts of the atmosphere at all times. As you get closer to the surface, that kind of dwindles, but it's a very hostile environment. But what we see is, if we look at the initial composition of these atmospheres, Venus, Mars, original Earth, carbon dioxide, nitrogen, and oxygen, they supposedly had very similar atmospheres early on. Earth now is radically different. So Earth's atmosphere is primarily nitrogen, 78% nitrogen, 21% oxygen. The difference is life. Life made this oxygen, life altered our atmosphere. Venus didn't have that. Why not? Who knows? So let's look at the surface of Venus. So it's again, it's very similar to the moon. We've got highlands, we've got plains, we've got lowlands, very similar to the lunar surface. There's these tesserae, which might be kind of rift zones where the planet was actually sort of kind of tectonically pulling apart. There's also these areas of pancake-like volcanoes, which are called coronae. One thing that's interesting about Venus is that one of our relative dating techniques, the crater density should be higher on surfaces that are older. What we see is that over the surface of Venus, the crater density is relatively consistent, relatively equal. There are some places where it's a little bit different, but the vast majority of the Venus surface is relatively consistently cratered, which suggests that it's relatively consistently the same age. And so it's been suggested that Venus catastrophically resurfaced. Almost the entire surface was redone. So something caused a lot of volcanism or some mechanism that the crust was completely turned over about 500 to 700 million years ago. There's currently no active tectonics on Venus, but there is volcanism and there is convection. And that may be what's actually causing this resurfacing. So we talk about Venus exploration, not a lot. High temperature, the fast circulation, the really fast wind speeds, the thickness of the atmosphere, observation's really difficult. And also, we know that it's that uninhabitable. Why would we bother looking? So the Soviet Verna 3 was the first to land on another planet. It was supposed to land gently. It crashed instead. The 9 landed and actually transmitted photos. So again, this shows that like at this time, this was after the Apollo missions. In many ways, Russia was still ahead in some aspects. There's been a total of 42 missions to Venus, but nobody's landed on it since 1984. Again, because it's difficult, it's inhospitable. But NASA and I guess most of the other space federations on Earth have been kind of following this follow the water exploration strategy. One of the main reasons why we're exploring outer space is we want to find evidence of life outside of Earth. We know that, or we make the assumption that life requires liquid water because pretty much all life on Earth requires liquid water. And so life as we know it requires liquid water. So if we're looking for life as we know it, we need to look for water as we know it. Now, that's kind of ruling out the idea that maybe there is life that is not as we know it, but that's another topic for another day. But we've been making that assumption, and so Mars is much more attractive. Mars is much more likely to have liquid water, and so that's kind of been our major focus. But one thing that's interesting about Venus is that the Martian surface, we know the conditions. It's cold. There's no atmosphere, so it's really low pressure. It's not a breathable atmosphere. The surface of Venus is highly inhospitable, but there's a place in the atmosphere up in the clouds where as you get further and further up in the atmosphere, the pressure drops and drops and drops until eventually you're in outer space where the atmosphere is zero. There is a point in the Venus atmosphere where the temperature and pressure conditions are essentially equal to the temperature and pressure conditions on Earth. So one kind of wild theory is that instead of populating the Martian surface, it might actually be easier to build like a cloud city in Venus up in the atmosphere. The surface would still remain basically, you would never venture down there. But in theory, we could live in the atmosphere maybe even easier than we could on the Martian surface. So kind of keep that in mind for the future. And then if we look at Venus stratigraphy, again, because of that thick atmosphere, our resolution of the mapping is really low. It's about 75 meters per pixel. And the history is kind of wiped out by that big resurfacing event. So there's not really a ton known about the stratigraphy, but we use these same relative dating things. We're kind of running low on time, so I'm just going to get into Mars. So Mars is heavily explored. We've had vast amounts of probes. We haven't put a person on Mars, but we have had rovers roving around. The opportunity is still out there running around now. But one thing that we've been sort of pleasantly surprised by is that the Martian surface has a lot of features that are strikingly similar to Earth's surface. This is a picture from Mars. If I didn't tell you that, you might just think that it's someplace out west. You see strata. You see things that resemble the stratigraphic processes on Earth. The big features on Martian surface here, the Valles Marineris, the big central rift system. You can actually see some major craters that are actually offset along that rift system. There's also this big Tharsis volcanic province over here, very high volcanic area. And then just a little bit off of that is Olympus Mons, the largest known volcano in the solar system, and therefore the largest known volcano anywhere, because we don't know of any outside the solar system. I'm sure there are some, but we don't know that. So Mars expeditions, again, essentially a massive history, 55 missions in total, but a really high failure rate. Less than half of them actually succeed. Again, this trend of the Soviets kind of getting there first, but they actually failed most of the Martian missions, and so we were the first successful one. Mariner 3 was the first successful flyby. The first successful impact, if you want to call it that, was the Mars 2, but it again crashed. And the Curiosity rover is still roving around out there. It's still active. Opportunity went like well above its record, its intended mission span, but it did finally lose contact last year. But again, this is kind of the future vision here of a colony on Mars's surface. Martian stratigraphy, again, we have a lot of data, we have a lot of constraints, but we also understand a lot more. And so if you look at a geology map of the Martian surface, it's quite complex. Again, we still don't have any rocks, though. We have never brought back Martian material. We do have a couple meteorites that have landed on Earth that may be from Mars, but we don't have any actual rock samples that we actually collected in situ, in stratigraphic context from Mars. But again, we've constructed this stratigraphic history with its own unique Martian names, the Noachian, the Hesperian, the Amazonian. What you'll see here, volcanism, just like the other planets, craters, just like the other planets, basins, just like the other planets. The one thing that's different here, it says fluvial activity. There's valley networks on Mars. Are these fluvial river valleys, or is just something that very much resembles them? We're not quite there yet to definitively say, but I'd have to say it's about 95%. These kind of things, they're not consistent. They kind of come and go. But there are times in Mars's history where they're quite common. Are they actually surface water flowing rivers like we would think of on Earth? Or are they just outflow meltwater during the summer? The subsurface ice would melt in the warmer summer and kind of be expelled and flow as liquid water on the surface as these like ephemeral, short-lived, very low duration streams. Is that what's happening? We don't really know yet, but we're kind of getting there, I think. But again, the thing that's very interesting about Mars and the thing that really sent us there is that there's a lot of things that are nearly indistinguishable. Again, this is Mars. This is that fluvial system. Is it a river system? We can't say for sure, but it sure as hell looks like one. If you didn't see the craters here, you would just assume that this was Earth. That, okay, yeah, this is a river system, a typical river system on Earth. One problem with that is that there's no known liquid water on the Mars surface. But the polar ice caps at the North and South Pole definitely contain a lot of solid water. The North ice cap is about the same volume as the Greenland ice sheet. Initially, it was kind of thought that it's just all CO2 dry ice, but dry ice is really just a minor seasonal coating, like a couple meters. It kind of melts away in the summer, comes back in the winter, but it's never very thick. The rest is all water ice, but it's not flowing water. There was some recent evidence of maybe a possible lake of liquid water underneath one of the ice caps. It's not confirmed, it's not known, but it's very likely. There's probably liquid water underneath the ice caps, and there's probably liquid water elsewhere. Before Mars's atmosphere was stripped away, there was probably lots of flowing liquid water. It's possible that Mars was wet at some point. That's what we're trying to work out now. But if you look at Martian geology, if you look at things we see, here are some spheres that they found on the Martian surface. Looks very similar to oncolites that form on Earth as a result of water activity and bacterial activity. There's some glacial banding in the polar ice caps that looks very similar to glacial banding that we see on Earth. And then if we talk about exoplanets, when I took high school Earth science, there were no exoplanets. There were no planets outside of our solar system. There were only 9 planets that we knew of. Pluto was a planet at the time. Now there's over 4,000. There's nothing special about Earth, nothing truly unique about it. There's nothing truly unique about the sun, other than we live here. The sun plots kind of right in the middle of the main sequence of stars. It's relatively ordinary from a brightness standpoint. It's relatively ordinary from a temperature standpoint. There's probably lots of rocky planets that are in the habitable zone of other stars. Why would we think we're the only ones that have life? Why would we think we're the only ones that have flowing water? Why would we think we're the only ones that have stratigraphy? We're probably not. So future classes, probably not before I retire, but maybe your children will learn about exoplanet stratigraphy in stratigraphy class. And sorry, I went a minute over. That's all we got for today. I hope you enjoyed that.